All right. Now, this week, what we're going to do, we're going to finish up the remainder of dealing with calculating conductor ampacities. And then we're going to get into sizing our overcurrent protection devices. And that'll probably take us for the next 3 to 4 weeks. And then we'll get into residential and commercial calculations doing the full ones. Now, this one we looked at last week, and this is where we would look at sizing for a single motor. In this case, we're doing a 2 horsepower single phase 208 volt. And you would, in order to take and get the amperage rating, I brought this up the other day. If you look at 430.681, it tells you anytime you're sizing the conductors or overcurrent protection device to use the amperages that are in the tables, 430.247.250. In this case, since it's single phase, we'll be looking at table 430.248. And if you pick up your 208 volt, come across, pick up 2 horsepower, that's going to give you 13.2 amps. And then 430.22 states that if you have a single motor here, you need to take it at 125%. So I'll take the 13.2 amps times 125% gives me 16.5 amps. Then just go over, look at table 310.16. It'll tell you the next size above that's a 14 copper conductor. Pretty
Yeah,
simple.
and one thing I want to add too is when you're doing these like on an exam, one thing I like to do, and you can, this is one thing I really like about James's illustrations, is you can take any one of these numbers and you can plug those in. So you can, if you have any of these known in the question, you could just take one of these numbers, you could plug it in, and you could see if it works out. Because if they ask you like what's conductor, then you could actually plug that into this formula. You could work it, and if it comes out to 14, then you know that any one of these numbers in this equation is correct. So
Sure.
I like to do that kind of reverse math kind of thing as to try to save you time, so you don't have to do so much calculation. You can just take one of the answers, plug it in, see if it comes out to 14. Take one of the answers of the question, plug it in. If it doesn't work out, that's not the right answer.
Correct. Simple, simple to do. And
Yep.
same here. Like I said, this is a three phase. It's 40 horsepower, three phase, 460 volt design B. In that case, we'll be in table 430.250. You pick up the 460 volt, come down, match it up where your 40 horsepower, tell you it's good for 52 amps. You got a single motor, 430 24 or 22. Take it at 125%. That gives you 65 amps. Go to table 310.16. 75 degrees C calm, and number 6 is good for 65 amps. Pretty simple.
Right.
It's the same
Yep.
concept. I didn't change. It just depends what table you're using at that point. And for
True.
single phase, 432.48, three phase, table 430.250. All right.
Right.
Then if you got multiple motors, you heard me talk about this last week. I said you take the largest motor 125%, everything else is at 100%. Well, we kept it pretty easy where you could go find everything. You got a 40, 50, 60 horsepower motor, it's 460 volts, and it's three phase. Pick up the 460 volts, come across for a 40 horsepower, tell you it's good for 52 amps. A 50 horsepower is good for 65, and a 60 horsepower is good for 77. Well, naturally, the 60 horsepower is the largest, so we're going to take that 77 amps at 125%. It'll give you 96.25 amps. You could just round down if you wanted. If I was over zero point 0.5, I'd round up to 97. But anyway, you 96 or 96.25, whatever you wanted to use. Then you got 65 and 52. You take both of those at 100%. Add the total up, gives you 213.25 amps. Go to table 310.16. I pick up the 75 degree C column. The next amperage above that's 230 amps, which is a 4-aught conductor. So
Right.
if you notice, any single motors, you take at 125%. You have additional motors, you take them all at 100%. Add them all up
Right.
together and you size your conductor. Pretty
Yeah,
simple.
and the one thing that you have to realize, like when you're in this exam, if you go back to that illustration, James,
Mm-hmm.
a lot of these a lot of these questions, when you look at these illustrations, that looks overwhelming. Like you see how James puts all those code loops in there. There's all this stuff to think about. That's really not that overwhelming when you just start dissecting it down, little piece by piece, and don't let yourself get overwhelmed on that test. Just say, hey, I got this. I'm going to start with my largest motor and start narrowing down what you need to do from there. So that's a really good illustration, James. And I just don't want people to get overwhelmed when they see that. That's what happens on the test. You get freaked out. You get scared. You see all these numbers and you don't know how to factor them. Just start with your largest motor, work your way down, come up with the right answer.
Sure. And we even prep you. Like we got in the, we got feeder protection. We're telling you, look at 430.62A and 430.63. We're going to get to that probably in about 3 weeks. And we're going to show you to tie all this back in with the sizing of the conductors. And you're going to see it's really not that hard to do. All right. Okay. Now, here you got phase converter. And when you go over and you look at sizing the conductor in 455.6A2, it's going to tell you got a fixed specific load here, and it's going to tell you to take it at 250%. But it's also going to tell you have to protect the conductor, or you have to protect the amperage rating that's there. Okay, so that means I'm not going to go down. I'm going to actually size those conductors up at that point. Okay, and if you go over and you look at a 25 horsepower motor, I'm just still going to, in this case, I've got a 3-phase, 230 volts. So I'll go to table 430.250, come down, you'll pick up your 230 volt, come across, pick up 25 horsepower. It'll tell you it's good for 68 amps. And then it'll tell you in 455.6A2 to take that at 250%, which is going to give you 170 amps. Then you go look at the next size above that in table 310.16, and that's going to be 175 amps, which is a 2-aught copper conductor. Okay?
Right.
So pretty basic, staying the same. Here's an AC unit. Now, when you deal with an AC unit, they're going to tell you right up at the front that you're going to use the nameplate value. You're not, and why are you going to, first of all, let's discuss why are you going to use the nameplate value? Well, the reason is because this is an appliance. And in other words, what is that? What that is, that means it's what? A listed assembly. It's all contain one. So you're going to use the nameplate value right here. So I have a compressor of 19 amps and a condenser of 2.5. That is the main important information you need here. Now remember this. Right. You're going to still take one motor at 125% and all the rest are added at what? 100%, which you'll really see that in the next illustration. So the largest motor here is the compressor. So I'm going to take it at 125%. That'll give me 23.75 amps. Then I'll take the condenser, which is 2.5 at 100%. So that's 2.5. Add that together, it gives you 26.25 amps. Then I go to table 310.16, and the next size above that in the 75 degree C column is 30 amps, which is a number 10 copper conductor. Pretty simple.
Yeah, and what you're going to realize is that AC unit is only going to draw a maximum of that ampacity. Mm-hmm. So that's how they actually make the nameplate. So a lot of people don't realize that they actually use that same math to do the actual what it says on the nameplate. Just because they say 26 amps or 25 amps or 24 amps doesn't mean that unit is going to draw that amount. Like that's your 125% calculation. So you have to keep that in mind as a reference point.
Yeah. And if you look at this, we did a one-line diagram, but we show you 3 different types of AC units here. We got one that has a compressor of 40 amps, a condenser of 3 amps. Then AC unit number 2 is 25 amps with a condenser of 2.5. Then AC unit 3 is 23 amps with a condenser of 2.5. Well, the largest compressor there is 40 amps. So I'm going to take it 125%. and then I'll add the 3 amp condenser, which gives me 53 amps. Then I take the 25 amps and the 2.5 at 100%. That gives me 27.5. Then I had the 23 amp and 2.5 amp for AC unit number 3, and that'll give me 25.5 amps, and that all was taken at 100%. So I still only took the largest. Everything else at 100% gives me 106 amps. Then I go look at table 310.16, 75 degrees C column. The next size amperage above that's 115 amps, which is a number 2 copper conductor. So,
Dude, that is one big unit if you're doing a number 2 to that thing.
yeah, I think that's a feeder going over there.
Oh
Okay,
man, only if you put pieces in there.
now this one is looking where you got a 2-wire primary to 2-wire secondary of a transformer, and this is just confirming what we have up there. So I have an upstream overcurrent device of 50 amps, okay, and we're showing you the downstream at the panel from the transformers 100 amps, and we're telling you we're running number 3 THWN. Well, how do I know this is correct? Well, if I take 240 volts, divide it by 120, and then multiply that by 50 amps, it gives you 100 amps. So therefore, in order to protect those conductors and panel from that transformer, I would need number 3 conductors that will protect for the 100 amp overcurrent device. And the 50 amp overcurrent protection device on the primary side is protecting the secondary conductors and panel boards on that secondary side. Okay? And that's just proving what's there. Now, here's the 3-wire. Now, when you look at this and you start sizing the transformer going over there, let's look at what we got. We have a 480 volt 3-phase. We got 80 amps of continuous load. I'm sorry, 90 amps of continuous load. And you come in and you start looking at everything that's here. They're also going to tell you we got 208 volt, 120 volt secondary and a 75 kVA transformer. Well, first thing I have to do, and we did this at the very, very start when we were doing formulas, and I was telling you how to get the amperage when you had kVA rating there. Well, I've got 75 kVA times 1,000, and I'm going to divide it by 240 volts. Okay. Now, I take and do that 240 volts. That's going to give me 312.5 amps, and then I'm going to do the primary side conductor size here. So I'm going to take that at 125%, and that's going to give me 390.6 amps, which if I go over and look at table 310.16, the next size above that's 420 amps, which is a 600 kc mil conductor. Then I look at sizing the overcurrent protection device for that primary. How am I going to determine that? Well, go look at 240.4B. I'm not exceeding 800 amps. So therefore, I'll have a rule of thumb when we get over at overcurrent protection devices that I'll tell you anything at 125% or less, go up to the next standard size. And then any percentage above that, you're going to drop down. Okay. Now, the only difference in this 125% here is I didn't exceed 800 amps. So therefore, that means I'm going to use the next standard size per table 240.6A, which is going to be a 400 amp overcurrent device. Okay.
Yeah, and just to get a little disclaimer out there, we're not saying you have to always drop down. It's just a rule of thumb. Like, you can go up to the next standard size, but it, like we always say, like, why would you? You know?
Yeah. And here's a good one, and this gives you a little off thing here. If you look at the secondary, I got a 75 kVA transformer, and I've got a 208 volt secondary, and it's 3-phase, so I'll take it at 1.732, and that's going to give me 360 volts, which will give me 208.3 amps. And if I go look at table 310.16, the next size above that is in the 75 degree C columns, 230 amps, which is a 4-aught conductor. So if I have a 208.3 amp for the panel board right there, what size overcurrent protection device would I need? I'd need a 225 amp overcurrent device.
Right.
Okay. So that's how we go about sizing that.
And you have to be careful too in that instance because not always do you need a primary and secondary overcurrent device.
No, you don't. All that is showing you how to do the conductors and how those
Right.
conductors dictate the size of that overcurrent device.
True.
Okay. And then this is a capacitor. Okay. I've got um, 25 kVA capacitor. It's three phase, 208 volts, and the conductors are 3 aught. Okay. Now, as I look at my 3-aught conductor and I go look at table 310.16, there's two calculations here, and you're going to do it based on the largest calculation. So you can take the conductors at a third. So if I have 3-aught conductors and I look at table 310.16, 75 degrees C calm, it's going to tell you third gives me 67 amps, and 67 amps is going to require number 4 conductor. Okay. Now, the other way I look at this is I can do it based on the full load current of the capacitor. Well, I've got a 25 kVA capacitor, which will give me 25,000 VA there, but it's a 208 volt 3-phase. So 208 volts times 1.732 will be 360 volts. You'll divide that into the 25,000. That's going to give you 69 amps. And then you go look at 460.8A, it tells you to take that at 135%. So I take the 69 amps at 135%, that's going to give me 93 amps. And the next size above that in table 310.16 is 100 amps, which is a number 3 conductor. Well, based on those two calculations, the number 3 is larger than number 4. So therefore, the size copper conductors are required to be number 3. Okay. Now, as I go in and I look at welders, this is very simple. All you need to keep in mind here is you need to go get the multiplier. Okay. Well, we're going to give you some known values here. You got 89 amps of load and you got 80% duty cycle. Okay. And we're going to size THHN. Now, the welder's 89 amps. And then if I go look at the duty cycle for 80%, it's going to tell you that duty cycle for the multiplier is 0.89. So I'll just take 89 amps times 0.8, going to give me 79, and I'll look at 10.16, 75 degrees C column. The next size above that's a number 4, which is good for 85 amps. Okay, very simple. Now that one right there is for a non-motor generator. Now watch this. I go to a generator or I'm doing the exact same thing. I have the welder 65 amps. If I go over and pick up the 80% duty cycle or an arc welder, it's going to tell you the multiplier is 91%. So I take 65 amps times 0.91, that'll give me 59.15. Then I go look at table 3 again in the 75 degree C column. The next size above that's a number 6 conductor, which is good for 65 amps.
Did you forget to switch? Okay. No, you know, the problem I have with this one is, you know, it looks like that's hardwired there.
Yeah. Yeah. Well, if they use it outside, I guess it needs GFCI protection. Okay. And then this is the same thing. I've got a 100 amp resistance welder, 40% duty cycle. I'm going to go over and look at sizing the conductors at 630.31A2. And you're going to see in step 1, the welder's good for 100 amps. For my 40% duty cycle, I find my multiplier, which is 0.63. Take the 100 amps times 0.63 gives you 63 amps. And then like the last problem, table 310.16, in the 75 degree C column is 65 amps, which would be a number 6 copper conductor. Pretty simple. And so it didn't really matter in all of these that I'm doing. You're still doing the same type of steps. You got to get your multiplier that's going to go with it. And if I had a single motor, 125%. Didn't matter if it's single phase, 3-phase. All other motors were taken at 100%. I got an AC unit, use the nameplate value. You take 125% for the largest single motor. If you had multiple motors, all the rest are taken at 100%. And then when I get here to welders, everything is taken by the nameplate of what the welder is, and then you get the multiplier inside your conductors. Pretty simple.
Right. True.
All right. And then this is just a clarification of what we looked at last week when we were dealing with these type of controllers. And I was saying, like, this is a start and stop station on the cover, and it's inside the controller. So that means it's in free air. Okay. So when you go down and look at the notes and you look at table 430.72B column B, it's going to tell you in the note that you're going to be looking at table 3.17. So my overcurrent protection device upstreams 80 amps, and 80 amps will permit a number 14 conductor. Now, in order to prove that point, a number 14 conductor is good for 25 amps per table 310.17. Then it tells you down in the note to take that at 100%, and that'll give you 100 amps. And they're telling you 100 amp would be permitted on the 14 conductor. Therefore, that 80 amps is permitted because it'd allow you to go all the way up to 100 amp. See there?
Right.
So
Yeah,
it's just
that's
establishing the fact even further. And then when I go to a remote type, now you're going in conduit over. So now you're not in free air. So when you look at the column C and pick up the notes below it, it's going to tell you you're going to use table 310.16 because you're in a raceway. So
Right.
it says here a 50 amp will permit what? A number 12. Well, how do I approve that? Well, all I got to do is look at sizing the conductors, and it's going to tell you that that number 12 requires what? A 20 amp overcurrent protection device. So therefore, a 50 amp is permitted to protect that number 12 conductor.
Right.
And it's very simple. All they're doing is clarifying that calculation is correct. That's in the table.
Right.
That's all they're doing, and we're showing you how they did it.
I really like that 31017 that we referenced when we were doing the free air. I think we did one on bundling inside a panel enclosure. And
yeah, that was one nobody had brought up, and I brought that up. Actually, somebody messaged me, and they go, "Damn, I never thought of that." They go, "That is correct, isn't it?" I said, "Yeah, that's correct."
Yeah, that was cool, awesome. Big kudos to old Stallcup, another hook 'em horns. Everyone just do a hook 'em horns
baby.
to their
Hook
'em horns to their screen right now for old Stallcup.
They need to support me. They need to be a sponsor. I'm gonna call the University of Texas and tell them.
Hook 'em horns.
Now this is a control transformer at 1.5. Now, when you go and you look at this, there's that when you go over and look, 725 point something. I'm trying to remember the exact section over there. But anyway, they allow you to go to 300%. But when you come over here and look at 430.74, they allow you to go all the way up to 500%. Okay,
Right.
and they're telling you here, I can have basically what Mac, but that's how you look at it. So if I took 1.5 at 500%, it's going to give me 7.5. They're basically just telling you that number 14 will handle that 7. So even if I did it at 300 or 500, it would still hold the load that's there.
Right.
Okay.
You're kind of breaking up a little bit tonight, but you know, like I
why I'm
said,
breaking up. I'm sorry about that, y'all. If I'm breaking up.
Just a little choppy. It's no worries, but like I say, if you have any questions, feel free to hit us up, and we'll explain it in more detail.
Yeah, our internet is funky around here for some reason. We have to come out and redo everything, and that was great. And we're having problems. But anyway, here's a 20 amp overcurrent device. This is where you're going over. You got your fluorescent lighting that's there. And we're just showing that, yeah, this is a fact that I've got that determine my protection, and can the number 18 conductors be protected by a 20 amp overcurrent device, and the well, sure, because your fixture wire is permitted in the whip to be number 18, and that 20 amp will protect that, plus the number 12 conductors that are going over there. And another section I would reference here is 240.4D, which also deals with small conductors. Okay?
Right.
And then your last is where I'm going over to a pole, and this is just like a question, really, but can the number 16 conductors be run 55 foot and be connected to conductors that are protected by a 20 amp overcurrent device? Well, sure they can. And that's where you're going to go over, and you're going to look at 240.5B2 for the length of the conductors, and 410.30B is where we're looking going over feeding this outside lighting. Well, that the reason I'd have number 6 conductors going over because I'm calculating for voltage drop.
Right.
Okay. And what we were trying to point out here is just you get a question like this and you see something where it says connect the number 6 conductors, and you're thinking, why the hell are number 6 conductors going over? Well, this is why, because they're having to increase the size of conductors going over due to voltage drop and connecting it to a 20 amp overcurrent protection device.
Yeah, but like if you put like a J box out there, you only need a number 12 pigtail.
Well, you could actually take and you could go to one light that's out there, go to a box out to a point, and then you could actually have a different size conductor going out from that point. You would calculate the length of each one of those at different intervals. I've actually seen that before because they were going to have problems making a connection to the overcurrent protection device.
Yeah,
so they had to figure out a way to do that.
Your bonding conductor to that junction box is going to be sized off that largest size entry.
Well, all to the first one. If you had another one, it'd be sized off what was going to that. Yeah.
Yep, I agree.
Okay. And it's interesting. I actually think I'm gonna have to do some calculations for my son-in-law and my daughter. She's it looks like on their property they're gonna my father-in-law, ex-father-in-law, he owned Mueller Buildings. And he is going to help them. They're going to put a building out there, and that's going to be her new yoga studio. And I told her, I said, what you're making, I said, if you just put, $5,000 a month on it, I said, it's going to cost you about $100. Within a year or two, you'll have it paid for, and everything's pure profit at that point. And she's looked at doing that. All right. Now, this is going to get us into overcurrent protection devices, and I'm going to give everybody a rule of thumb before we start this. All right. And I'm going to prove this as we're going through all these calculations. Now, this is something I did on NEC Live. They had me on. They wanted me to do conductors and overcurrent protection devices, and they wanted me to mainly do calculations. And one of the statements I made is if you size me at 125% or less, you're going to go up to the next standard size overcurrent device. Any percentage above that, you're going to drop down to the next standard size overcurrent device. You need to remember that little tip. Now, the only 2 places that doesn't hold true that I'm aware of at this point is phase converters. As we were looking at the other one where you size it at 250, you're going to have to go because you got to protect the conductors. They're sizing that conductor that way. The other one is transformers, and transformers gives you the option to go up or down because when you go down and pick up note 1, it's going to say shall be permitted. That means you have the option to go up or down. Okay? Nice. And back probably 2 cycles ago, it didn't even say that. It just, you just went down, and then if you were at 125% or less, you went up. Okay. But I'm going to show
Okay.
you why y'all look at the tables and everything as we go through this and the wording, you'll understand what I'm telling you is true here. Now, the first problem we're going to look at, we're going to size the overcurrent protection device, and this is going to be for a branch circuit with a continuous load of 25 amps with 75 degree C terminals. Okay, so if you go look at 210.19 A1A, we'll size basically the conductor here. Okay,
Right.
now you take 21.5 amps times 125% gives me 26.875 amps. You can leave it there, just go round it up to 27 amps. Now, as I look at sizing the overcurrent protection device, you're going to see the same in 210.20A, and it's going to tell you got a continuous load. Then I look at table 240.68. The next size above that is a 30 amp overcurrent device based on the calculated load. Now, I want to point one other thing out, and you can put these sections all together. This is another code loop. You can put 210.19A1A, 210.20A. Okay, now that's for branch circuits. If I look at feeders, I can look at 215.2A1A and 215.3 for the feeders. And then when I get the services, you look at 230.42A1 and A2. Okay. But what you're going to see, they're all going to say you got continuous load, you take it 125%. Non-continuous load, you take it what? 100%. Okay. So
Yeah,
even though it's go ahead.
I like how you put that 110 14 C1 in there,
Mm-hmm.
C1A, because like if you don't know that terminal rating, then you have to go up to 60 degree C column.
That's correct. And that's why in the problem up there, we tell you 75 degree C column. So if I was sizing the conductor here, it would be a number 10. Okay.
Right.
But it could be different if it was 60 degree C terminals. Okay.
Yes, sir.
That's on the problem we told you 5 degree C to get just sort of kick everything off. All right.
Yes, sir.
You got another one here. It'll be your problem. You got a branch circuit load of 23.5 amps. It's continuous. You know, you take it at 125%, and then you're going to size off that. We tell you up in the formula requirements that the terminals are 75 degrees C. Okay? So, everybody, that'll be your exercise problem. Shouldn't have too much problem with that. Now, here's where I'm getting with a branch circuit. I'm getting up in the amperage. Okay? But what you're going to see, it's very simple, but we did something a little bit different here to make you think about this. All right. Now, you got a continuous load of 100 amps with 75 degree C terminal. So we'll just look at doing the conductor. All right. You take it at 125%. That's 125 amps, and it can be terminated at 75 degrees C. Now, if I go look at table 310.16 and I pick up the 75 degree C column, it's going to tell you need a number 1, which is good for 130 amps. Okay.
Right.
Now, watch as I go down to step 4. How am I going to size the overcurrent protection device here? Well, I can take and do 2 options here. But if you look, if I look in table 240.6A, do I have a 125 amp standard overcurrent device listed there? Okay. You could be looking at protecting the load, or I can protect what? The conductor. So what
Yes.
you want to do is go look at 240.4B, and you'll have in parentheses there, it says it can protect the conductor. In this case, I'm going to protect the conductor, and I have a 130 amp conductor. So the next size above that for table 246A is a 150 amp overcurrent protection device.
Yeah,
Okay.
and it's probably hard to protect the load if it's unknown.
Yeah, that's what I'm saying. There's, I know what you're talking about. But when you get in, you start looking at these things. These are things you have to consider based on the conductor, and that's why 240.4B is written that way. And if you remember when we started all this, I actually went over all the terminals and everything and explained that. And there's a reason I did that, because I wanted you to be aware of how those terminals apply. And when it comes to, when we got to this point where we were going to size the overcurrent protection devices. So
True.
basically what I've done everything in a step-by-step format to get you up to this point. I just didn't
True.
cram it all in your mind at one time. Okay? So
Yeah, I just use adjustable overcurrent devices on everything, so
yeah,
it's all good.
and wonder if you need size of equipment ground larger or not. Okay.
Dude, I'll tell you what, like that is sad for whatever crew that was that asked this gentleman a question on his podcast that had to go repull their equipment ground because they had it turned up by a couple amps.
Oh yeah. Well, here's a good one. Branch circuit load's 90 amps. It's continuous load, and you'll see in the formula requirements you're going to size it based off 75 degree C terminals for your homework. All right. Now, here's a feeder. Now, I brought this up. I said, when I get to a feeder, it doesn't matter. I'm still, if it's continuous, I'll take it at what? 125%. It's just larger numbers. And in this case, I'm going to parallel it four times and terminate it to 75 degree C terminals. So I'll calculate the load once again. And if you look at 215.2A1A, that's for conductors there. So I take 724 amps times 125% gives me 905 amps. Now, even when I go over and I'm sizing based on the overcurrent device, I'll still look at 215.3. It's got the same wording there for sizing for continuous. So the 905 amps can be terminated at 75 degrees C. Now, if I go look at table 310.16, I need to get above that 905 amps. Okay. So if I pick it up and I'm paralleling it four times, the 4-aught is good for 230 amps. Parallel that four times gives you 920 amps, which is larger than the 905 amps of calculated load. Now I have to size the overcurrent protection device. Well, remember 240.4B deals with overcurrent devices 800 amps or less. 240.4C deals with overcurrent protection devices over 800 amps. Well, it says that the conductors have to be equal to or more than what the size of the overcurrent device is. So that means I have to drop down. And when you go look at table 240.6A, the next size below that will be 900 amps, but it's not listed. It's a non-standard type overcurrent protection device.
Okay. Awesome. Oh, welcome in, Bridget. Oh, awesome. Yeah, one of the A-team just showed up. Awesome.
A-team's in the house. Damn.
Yeah, great to have you in, Bridget. Awesome.
All right, and here's a feeder going over to a panel board. We're going to size it four times. The load's 678 amps. It's continuous and 75 degrees C terminals. So just take that 678 amps at 125% and start sizing your terminations based on table 310.16 to get the total amperage, and then you can size your overcurrent protection device. Okay?
Okay.
Now, here's one. I'm doing a tap. Okay? So I'm going to ask you what size overcurrent device is required for a 10-foot tap from a junction box that is supplied by a feeder with a 500 amp overcurrent device that's upstream. Okay?
I'm going to go 10%, Bob.
Everybody remember what I've said on this. When you're doing taps, anything 10 foot or less, I divide by 10. Anything over that 10 foot, you take at a third. And if I did a tap with a transformer in the tap, you still do the primary at a third, but the secondary, you got to do it at a third with the ratio of the transformer. Okay?
Right.
So looking at this, I've got a 500 amp upstream overcurrent device divided by 10 gives me 50 amps. I'm going to terminate this at 75 degrees C, which is a number 8 conductor, which is good for 50 amps. Okay? So basically, the very minimum that tap can be is a number 8 rated at 50 amps. And then, of course, you look at table 240.6A, the 50 amp matches up with the 50 amp for the conductor size. And therefore, the very minimum that tap can be is 50 amp overcurrent device with number 8 conductors. Okay? Now, let me state this. If I take that tap all the way up and tap off of that at 500 amps, it's no longer a tap at that point.
Right.
Okay. Anything from 50 amps up to that 500 amp is a tap.
Okay.
All right.
Yeah, and it's really awesome because I just want to let Bridget know we made a video for Chris, so we're gonna do the video for Chris. We just I think James forgot he was gonna do it earlier, but
I sure the hell did. Hell, let me go ahead and throw it up right now.
all right.
Or you want to do it after? We're almost done.
Yeah,
With
just do it when you're done. I know you're almost
Okay.
there.
So here I've got a 600 amp, 10-foot tap. Terminals are 75 degrees C. I'm going to divide by 10 and then work it out from there. Okay. So, but what I like to point out, we did this on conductors a couple of weeks ago. And if you notice, I'm still doing the exact same thing. I'm not changing anything on the way that I do it. All I did earlier, we size the conductors. Now we're doing the overcurrent device and telling you what the minimum size conductors and overcurrent protection device would be. But you're still performing the exact same type calculation.
Awesome.
Okay.
All right, Brandon in the house. What's up, brother? Oh, awesome, man. The whole crew's rolling through tonight, man.
Yeah, bring them on. All right.
Awesome.
Now, if you look, this is a tap from 10 foot to 25 foot. I said all other taps, what do we take it at? A third. So I take a third of that 500 amp overcurrent device that's upstream. That gives me 167.5 amps. I go to table 310.16. The next size above that is 175 amps, which is a 2-aught conductor. Guess what? It matches up with a standard size in table 240.6A for the overcurrent device. So you would need at least a 2-aught and 175 amp overcurrent protection device would be your minimum for that 10 to 25 tap.
Nice.
Okay. Very simple. And if you notice, when I did the conductors a couple weeks ago, I did this exact same calculation. Now all I'm doing is matching up the overcurrent device to match up with the conductor.
Dude, I'm telling you, you got some major hate mail on NEC Live when you did that, and it was funny because I was blown away. Like there were so many people like, you can't do that and stuff. It was funny.
I'm showing you. All you got to do is go read the section.
Yeah.
What's funny as I was doing it, Derek was telling me, slow down. I can't keep up. He couldn't get those sections quick enough.
Yeah.
After he told me, he goes, I'd heard y'all could do that. He goes, I've never seen anybody just make questions up off the top of their head and just blah, 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 blah. I'm like, well, hell, as long as we've been doing it, I should have learned something within the last 30 years.
Dude, when you were doing like the 9 amp transformers and stuff, that was pretty good. I was like, whoa, I was even blown away. I was like, and then all of a sudden it was funny because they're like, hey, Bill Snyder has a question. Next thing you know, you guys just started busting up laughing, and I was like, oh yeah, it's a good question.
But he's asking some bullshit. That's what he's doing. Oh hell! All right. Get back to it. So we got a 10 to 25 foot tap. The upstream overcurrent device is 600 amps. You're going to take a third, get your amperage in there, get your conductor size, and then size your overcurrent protection device. That's your homework. And then I come over here. I've got a 25 foot tap, but I have a transformer in it. And we're going to tell you that you have a 300 amp overcurrent protection device upstream. You have a 408 volt primary and 208 volt secondary. Let's see how easy it is. All right. So we already know what the protection is upstream. So all I need to do is the secondary. Well, I said, if you have a transformer in there, we have to get the ratio of the transformer, right? So you're going to take the 480 volts, divide it by the 208 volts, and then you'll multiply. Basically, you got 300 amp multiplied by a third, which is 100 amps. So you'll take the 100 amps time that multiplier is going to give you 230.7 amps, just rounded up to 231 amps. Now this where it gets interesting, because if you got the 75 degree C terminals, you go look at table 310.16. It just is barely over 230 amps, which is a 4-aught conductor. But sticking by code, the next size actually above that's 255 amps, which is a 250 kc mil conductor. Okay.
Okay.
So if I have 250 amps, I'm just going to protect the load that's there. That's 230 amps. I could put a 250 amp overcurrent device there.
True, because the load is known.
That's right. Load's known. All right. So it gives everybody, it shows you different, as we design our problems and everything, you notice we give you a lot of various things you have to think about. We just don't make everything exactly line up because we want you to understand you're looking at certain things here and you got to make assumptions here, and you've got a load that's given, even though I had to go up to a 255 amps for a 250 case of meal, the 250 overcurrent device would protect that 230 amp load. But on the other one, we decided to protect what? The conductor, because we had an overcurrent device that matched up right above it. Okay?
Yeah, and that's one thing that I want the students to know, that your overcurrent device can exceed your conductor,
Sure can.
but there's certain cases where it can't. So we just want you to know the different areas where, yes, in this case, the load is what you're protecting, and then in this case, you're protecting the conductor. So if that conductor ampacity is at a certain ampacity, you can't go exceed that.
Sure. And just remember, that is the minimum. I can still go up on my tap size if I want to. That's just a minimum. And then you could go up and have it match something, have the extra amperage there. All right. Absolutely. Now this one, you've got an upstream 250 amp overcurrent device that's given. Okay. In this case, we got a 408 volt primary, 208 volt secondary. Okay. So you're going to have to get the ratio of that. And then I'm going to take that upstream overcurrent device at a third. Then I multiply that all in, get my amperage, and go size my conductors and overcurrent device. That'll be the homework next week. All right.
Dude, I just wondered, go back to that illustration.
Yeah.
You got support for that J-box in there? I don't know. It doesn't look supported.
None of it's supported.
I'm just kidding.
Soon as I put a strap in there or something, showing it all strapped and everything, where's the sections at? It'd be giving me hell over that too.
Dude, you won't even have any room in your illustration. It'll just be solid black.
I know. I was going to say, there's only so much information you can put in an illustration. I mean, you can see we're using up a lot of stuff right there to make it look clean and all of that. And but yeah, I know what you're saying.
That's a good one though. That's a good illustration. I like it.
Oh, I think they're all looking great.
Brandon loved my comment. Yeah, I'm always busting his balls, Brandon. Always busting.
Quit busting my balls, Brandon. All right. This one's a 25-foot to 100-foot tap, and it's supplied from a feeder with a 300 amp overcurrent device. I said everything else that's left, you take at over 10 foot, take at a third. So I'll take the upstream overcurrent device at a third, which was 300 amps, gives me 100 amps. Go to table 310.16, which, in looking at the 75-degree C column, the number 3 is good for 100 amps. And then you go look at table 240.6a, you have a 100 amp overcurrent device. So your minimum overcurrent device is 100 amps with number 3 conductors. That naturally matched up. So look there, we've done a couple that didn't match, and we show you some that do match. Okay?
Right.
And here's we had an illustration just like this when we were doing the conductors, and all we're doing now is sizing the conductors and the overcurrent device to match. And you've got a 350 amp overcurrent device upstream, take it to third, get your amperage. Then once you have your amperage, know what your conductors are, and then size your overcurrent protection device accordingly at that point.
Right.
And that gets you, let me go through right here. I want to go through these secondary conductors, and then we'll call it the night. There's a few of them.
Okay.
So this in here, we're going to size the overcurrent device, and is required for a tap of 25 foot from the secondary of 100 kVA transformer. Now, remember, a lot of people, when we put this in there on purpose, we're telling you a tap on the secondary side, because a lot of people used to say just tap the secondary side of that transformer, when in reality, there are conductors on the secondary side of a transformer. Okay?
Right.
And Therefore, you're not taking at a third. A tap is where you're coming down from a feeder and tapping off of that feeder. This here is
Gotcha.
where you're just coming from the secondary side. So the secondary is 150 kVA transformer is supplied with a 200 amp overcurrent device having three-phase 408 volt primary and a 208 volt secondary. So I'm going to do the secondary here because I already know what the primary is. So
Right.
I have a 150 kVA transformer, take it at 1,000, and then you're going to divide it. Just get your amperage. So just like we did when we first started this Master and Journeyman at the first, what did we cover? Is how to apply these formulas for sizing your amperage when we were doing kVA. So I got 208 volt secondary. It's three phase, 1.732 for the three phase. That'll be 360 volts. Divide that in, gives you 416.7 amps. Then you go over and you look at table 310.16. What is the next size above that? I'm sorry, table 240.68. What's the next size above that 416.7?
Dude,
amps?
it's 420 amps, dude. Everyone knows it's 420.
Yeah, 420. So you got a 500 amp overcurrent device. Now, why would I go up? Well, if you standard size for the overcurrent devices that are rated 800 amps or less.
Right.
Okay. And that's pretty basic how you go about calculating this. Same thing here. We got a 250 amp overcurrent device upstream. Okay. And then what's my secondary? It's 208 volts. So I'm going to take the 360, divide it into the transformer, which is 200 kVA, get my amperage, and then I size my overcurrent protection device. Okay.
Right.
And that'll be homework for next week. Now,
Right.
This one, yeah, let me go ahead and get this because this is a two-wire primary, two-wire secondary, and we looked at that a while ago. So we got a 408 volt primary and 240 volt secondary. So how am I going to determine what the size of that primary overcurrent protection device is upstream? Well, all I'm going to do is find the ratio of the primary times the conductor ampacity. So I'm going to divide the 480 volts into the 240 volts, and I've got 225 amps. Well, I take that 225 amps is going to give me 112.5 amps, and then I'm able to drop down on the primary because I divided that primary into the secondary, and that overcurrent protection device would be required to be 100 amps. Okay?
Dude, I gotta tell you, James, I think I'm maybe being a bad influence because everyone knows it's all 420. So.
Damn. I think if I actually put that in the publication, I might get some kickback on that.
It's a Colorado thing, baby. You know, I can't deny it. You know?
Y'all need to cut that out. Y'all are starting to sound like Jeremy. And
Dude, I'm telling you, like,
and all them guys over there.
I think a Badger fan, like, I think he fell asleep on his keyboard. So
I probably did. But anyway, here's the next one. You've got the same thing. You're just going to prove that 50 amp overcurrent device upstream matches up based on your primary and secondary. Okay, and how did I get to 100 amp on that secondary based on the primary being 50 amps? We just did that a while ago in the calculation for the conductors that proved that 100 amp was correct for the number 3 conductors that are on the secondary side of that transformer. Okay. Sure. And then here's the 3-wire to 3-wire system. Exact same thing here. I'm just going to I've got a 400 primary, 240 volt secondary. And I look at my 500 kc mil conductors. What are they good for? 380 amps. Take the 480, divide it into 240, get your ratio, multiply it by 380 amps, gives you 190 amps, and then you just go up to the next standard size, which is a 200 amp overcurrent protection device. Pretty simple. Nice. Basically, we're just proving everything here at this point. How did I take here on this secondary and allow a 400 amp overcurrent protection device? Well, we're showing you the conductors are 420 amps. So I'm just going to take the voltage there and take the 240 volts, divide the 480 into it, take the 420 amps, and then size your overcurrent protection device.
Yeah, the
I see
420 amps. It
I
keeps
see
the
that.
motor going.
Okay. And with that right there, we're going to stop, and then we'll get into the transformers next week, really breaking down, showing how to size the overcurrent protection device.